Welcome to the Changing Channels podcast, brought to you by the Mile High Flood District and the Learning Community Advisory Council.
How's it going, everybody? I'm John Valines. I'm the Innovation Manager at Mile High Flood District. Just wanted to give a very brief intro to today's podcast so that you guys know why this is such a critical conversation to listen to. Today, I'm talking to Sean Young, who is the Director of AEC, Geospatial, and Enterprise Industry Marketing at NVIDIA. If you've heard the name NVIDIA, you probably own their stock if you have any money in the stock market at all. They're the most valuable company in the world, most valuable company in human history. You might not know exactly what they do. Long story short, and Sean's going to explain it later in the podcast, they build the technology that powers AI and everything else around modern graphics and visualization and simulation, digital twins, all of the stuff, the buzzwords that you hear people talking about in technology today. They are at the center of it. The data centers that are being built out all around the world, that's on their technology. And they have a perspective, and Sean has a perspective that really no one else that we hear from on a regular basis does about this stuff, and it's a critical one. Sean has worked in this field for 25 years. He has experience in 3D visualization and simulation across all aspects of AEC, automotive, manufacturing. He's worked at Autodesk on 3ds Max. He's worked at HP. He's led Omniverse at NVIDIA. He is just a wealth of information about this stuff, but you probably haven't met him before. So you're going to meet him now, and I hope you listen to what he has to say, because it's really critical for us at this point in time. So with no further ado, let's get into the podcast with Sean Young from NVIDIA. Welcome to the Changing Channels podcast from the Mile High Flood District and the Learning Community Advisory Council. My name is John Valines. I'm the Innovation Manager for the Mile High Flood District. My job is to kind of keep us abreast of the latest technology and trends that are going on in the world, and I do a lot of long-range strategic planning as well. But AI is a big focus, obviously, of any innovation manager right now. So that's why we're here today with a really special guest, Sean Young from NVIDIA. I'll let you introduce yourself, make sure we get your title right.
Yeah, hi, I'm Sean Young from NVIDIA. I take care of AEC and geospatial business.
Awesome. Yeah, so we're really, really excited, Sean, to have you. And thank you for making the time to do this. I know it's, we're not going to be a big customer of NVIDIA or anything like that. The most valuable company in the world doesn't have much to gain from a little flood district like ours, but we have a lot to gain from you and from your knowledge. And we really, really are grateful for this podcast and the prior conversations that we've had. And I've learned a lot from you already in the short time that we've been able to chat together. So I'm really excited for our audience to be able to hear from you the same kind of things that I've heard about what's going on in the world and AI and how we can prepare ourselves and our industry for where the world is going and where the world already is, maybe, in some other sectors. You do a lot of geospatial stuff all over the globe, I imagine, but here in the United States as well. What are some of the things that are going on right now that you think are really exciting, or that you hear being talked a lot about in the geospatial, remote sensing, AEC field? Like, what's at the top of your mind right now?
There's so much. How much time do we have here today? There's so much going on. It's really end to end. I mean, it's end to end in terms of the starting point is the data acquisition, and so where is your geospatial data coming from? Is it coming from sensors? Is it coming from cameras? Is it coming from LiDAR or satellite, like aerial or satellite data acquisition? And there's so much that can be done to expedite the data acquisition process and making sense of the data. And accelerating that whole process so you get the information more quickly. Because typically in this industry, it could be a week or longer between the time the data is captured and it's in some form that can be useful. Mm-hmm. Now, along comes AI, which is completely transformational for every industry, not just this industry. And AI can make sense of this mass amount of data. And if ideally, you want AI to work instantly. And AI, we've seen from our experience with ChatGPT and others like it works pretty darn quickly. That inference, you type in your prompt, you get a response in real time. If you want to be able to do that with geospatial data, if you have this lag between the time you capture the data and the time it can be useful for something like AI, if that's a week, then that is very disruptive to that process. It's also the case that AI needs to be trained, and AI is trained on that very same data. So you want to be expeditious in the way you capture that data, the way you process that data, and the way, including in that processing, you organize the data so that it can be used as training for AI. So you can have models that help you do the work. That ultimately these models, I know this industry is very algorithmically based.
Mm-hmm.
You use your algorithms that are maybe built into Excel files and such, which are good based on the way that humans have understood the past, but they're not necessarily the best predictors of the future, especially considering what's going on in our world today. Um, Things are changing in the climate so quickly. So having the ability for AI, which is like, think about it as millions of extra brains,
Yep.
taking a look at all the past data, at everything else that's going on in the world, and being able to make predictions on what might happen, it's a total game changer.
I think I think you're right, and that's something that our industry grapples with now is the fact that our models are empirical models for flooding, for instance. They're based on calibration to past events, and we look back at the period of record, which if we're lucky is 100 years or something like that on a big river, and we might see what we consider to be a 100-year or a 500-year storm, but we don't. And then we use those models to then try to predict with some level of certainty what's going to happen in the future. But with climate non-stationarity and other things, like you said, the future is not necessarily going to look like the past. And our traditional empirical way of doing engineering maybe is not suited to the world that we're living in, even now from a technical perspective. So I think our audience being aware that AI and accelerated computing are able to leverage data from around the world that may be able to tell us something about how maybe the climate is changing in our region, or what is a possible, future condition for the climate or for storms in our region. Those are techniques, hard science engineering techniques that were not available to us in the past, or when we learned how to do this work. There's new types. It's not just about doing the old things faster and doing the old things better. It's about doing potentially brand new science, brand new engineering that allows us to predict the future with greater accuracy and greater fidelity than we've ever been able to do before. And that's not something that we hear people talking about enough.
An algorithm is, very fixed. Somebody's idea, and it is static. It doesn't change. The only thing that changes are the variables that you put into it.
Right.
But an AI model is dynamic. It's trained on data, and the AI model can evolve. So you choose what data first of all, you can have reams of different types of data, multimodal models. So you can have climate, weather data. You can have all sorts of other environmental data. You can have water tables and whatever you can throw into the model. And the model then has its way of learning and predicting a future state. But what's really interesting is in inference time, the model can go and bring in other real-time data, which very different than an algorithm. The other thing is with what's called reinforcement learning, the model can evolve if it learns new tricks as it goes. So models behaving like a human would behave, but it has access to an infinite amount of data and an infinite amount of brains in the form of computer power.
Yeah. So what do you make of, if we are able to bring in more real-time information and data from various kinds of sensors, if we know what's going on in real time with the climate and with the water level and, ambient
moisture or soil moisture, whatever else people might want to throw into this thing to try to get a better result. There's a concern even just in language models about the black box nature of AI models and the fact that, we have billions of parameters. Right now, we might have an empirical equation that has 2 or 3 parametric knobs that we can turn, and we know that we're turning them because we're doing it manually, and we know at least what effect those things are going to have. The engineering mindset is very much that or civil engineering mindset, speaking for my cohort, is that if you don't know what knob you're turning or you don't know what the model is doing, it's not defensible. And even if we were to develop an AI model that gave us better outcomes, I think there would still be resistance among some people to trusting it because we don't know exactly how it's working on the inside. And I know that there's efforts to try to make language models and other AI models more not necessarily transparent, but to have a sense of where different threads of information lie inside of the neural network itself and stuff like that. How are these physical models that are supposed to be representing the real world evolving in that regard? And do you see any other industries that do design and construction or any kind of hard science engineering work that are moving into this realm more eagerly or that have seen success out there in the world? What are there any other examples that we could maybe learn from as an industry?
Yeah, so there's a lot to unpack
Yeah.
there. So um, first thing is, well, we just released an open source package of models and tools for autonomous driving called Alpamayo, I believe that's what it is. And we just released it last week. And it includes a world model, which is based on our Cosmos technology, which, if you're familiar with diffusion, like you type a prompt and an image appears.
Right.
And the image looks like the world. And now there's video models, video diffusion type of prompt, and you get a video. Well, that's good for entertainment purposes, but if you want to use that for some professional application, what you get back needs to be based on physics,
right?
Or mistakes are going to happen. And there's a lot to that, to making sure that those physics are accurate, because our world is pretty complicated. So the model, just like everybody listening to this podcast has gone to school to learn physics, the models that we create, we take to school to learn physics. So it understands the world, not just in a general sense, but in a specific sense, the laws of motion and et cetera. And so you teach the model that, but then you want to do a couple of other things. One, you want to test the model in an experimental, safe environment. So that's where a digital twin comes in. And in a digital twin, instead of bringing the model out to the real world right away, like go now do your thing, and it could potentially make mistakes, you test the model in this controlled experimental environment where you're simulating scenarios. And then the model does its thing, and then you can determine if it's right or wrong. If it's wrong, then you tell it how it's wrong, and that's called reinforcement learning. And the model,
like kind of how we're training vehicles and robots and stuff today.
Exactly. You train them in the synthetic environment, because in many cases, the place they're going to be operating in, like in the case of a robot that's going to be operating in a factory that's still under construction and doesn't exist yet. So you have to let it loose in this virtual world, like Tron, to go and do its thing, and you observe it, and you run tests with it, and then you build confidence until you're ready to let it out in the world. This Alpamayo model that I was telling you about, what it also does, it tells you what it's doing. It reasons, and that's on inference time. So it's trained to understand these things, understand physics, and understand what it's supposed to do. And then you tell it what to go do, and it's making a lot of decisions to get that job done, which is called agentic AI, agentic thinking. It's thinking on its own agentically. And so it might have to go and do additional research, call on a few different types of other models to help it make decisions. But you want to know, what's it doing?
Mm-hmm.
That's what you're asking. So in our Alpamayo, it tells you what it's doing.
In natural language.
In natural language.
Yeah.
It explains to you. Now I observe this, therefore
Mm-hmm.
I'm going to do this. So you can have that as part of your agentic solution. And as part of that reasoning process, you're able to pull in, as I mentioned earlier, real-time data. So like real-time sensor data. So this is everything I understand about the world based on how I was trained. This is my reasoning, and I'll explain to you what I'm thinking. But to make the right decision, I want to go grab that geospatial or that sensor data now in real time so I can make the right decision. I'm going to tell you what I'm doing and how I arrived at my conclusion. And here are all the sources for my data. When we publish a model, we also, an open source model, we also publish the data that it was trained on. So you can have confidence in the model and the weights that are associated with that.
So I feel like what I'm hearing you say is that the way that AI and engineering, and when I say engineering, it's kind of short for civil engineering just because that's our world. The way that AI and engineering could work going forward is less necessarily doing a specific task and saying, supplanting a hydraulic model with an AI version of a hydraulic model, for instance, but instead having kind of a partner in reasoning or a partner in your overall workflow that is applying logic and thinking and looking at multiple processes, maybe bringing in multiple models, data from all these various sources in the way that a human would if we had the same bandwidth and context and capability that these models do. It's essentially another partner that can reach out and kind of integrate a wider scope and context of information that we have been able to do in the past, and then bring that to bear to apply the same types of problems that we're already trying to solve today. It's not that we're going to have this off the shelf, here's how you do river modeling the way you used to do it, but now AI is doing it for you. It's really interacting with this larger agentic ecosystem that is enabling us to solve bigger problems and solve them faster than we could in the past. And it seems like the way that we're using, if you've used ChatGPT recently, you've seen that chain of thought type of reasoning probably. If you've used the thinking mode, where it shows you, well, it sounds like the person is wanting this, but here's the assumptions that I'm making, and you can go back and look at that if you want. That's the kind of thing that I think will give our industry some confidence that it understands what it's doing. And I could get in there and I could maybe reorient, change the direction that it's going if I felt like it was running off the rails, and it still has that human oversight element to it. So I think that's really interesting, a different way to look at the way that AI is applied. It's not just another technical tool, but it's really kind of a thinking partner.
And to that point, so right now in your world, you have a whole bunch of algorithms, some of which are incorporated into solvers, sometimes complex solvers. You feed in the data, you run the solver, you get the result, and it tends to be more or less accurate. It could take a lot of time to compute the response, depending on how much data and the complexity of the solver and such. Now, in the world of AI, what you do is called physics-informed neural networks. Are you familiar with that? Pins,
Yep.
Yeah. And the way pins an AI model, just like an LLM's trained on all the text of the internet, and then an LLM learns to understand language. A pin learns to understand physics, but it needs to be taught with data. Where do you get the data? You get the data from your algorithms. So you generate the results for specific use cases, specific data sets, like a specific river or body of water using an algorithm, and you feed those to the model and you say, based on these inputs, here are the outputs from the solver, but you don't give it the algorithm. Because that algorithm was generated by one human brain that had the same kind of input and output, right? And that human brain said, I think this is going to be able to resolve. Well, in theory, the AI can do a lot better than that one human brain.
Right.
So you teach it what that algorithm or solver knows.
With the inputs and the outputs.
The inputs and the outputs, and that's surrogate data,
Mm-hmm.
the results of that solver, and feed it all sorts of other data to support those different conditions you want it to be able to predict, and let it go and do its thing. Now, the very least, you should be able, and you could test, right? You can test it. You can take a new set of data, feed it to the solver, feed it to the AI, see if they come up with, you have a lot of confidence in the solver. The AI is learning. You keep tweaking the AI in terms of the training data you're feeding it and such until it gets the same accuracy as the solver. In some cases, you're going to start to see the prediction is more accurate. But in all cases, you're going to see the prediction is happening much faster because it's happening with inference instead of compute. And now it gets interesting because now you can start teaching that AI model new tricks and having it do real-time inference-based reasoning.
Yeah, being able to ask new kinds of questions that we weren't able to ask before. Yeah. And that gets to what you were just saying, I think points to some of the human side of this that I want to touch on a little bit, which is the types of teams and the types of relationships and the types of projects that are going to be needed to develop the kinds of things that you're talking about. Because I feel like right now we still have a pretty big gulf between the old school, in our world at least, we have the old school engineering folks who have done things the way that you're talking about, the kind of the empirical way, the way that they were taught. And then we have the tech world that is plowing forward in all different types of arenas to develop new ways of doing things. Those have to come together. Sometimes they're forced marriages, sometimes they're more organic. But at some point, there has to be a blending of the folks who have the domain knowledge and the folks who have the technical expertise to be able to build these new types of tools and make sure that they are as accurate and that they are, quality assured and that we have the right types of oversight and those sorts of things. And, that's the kind of relationship that I'm hoping to build with folks like you, is that we can start to talk about those kind of things and figure out how, where are the low hanging fruit? How do we start moving those forward? And I'm sure the same kinds of conversations are going on in every industry, everywhere in the world. But what does that mean in your mind for us and our little niche of what we do with stream and river restoration here, and our partners in other places in the country? Every city in the country has a district like ours that does something similar. What are your thoughts about how we can have some agency in the way that this future unfolds for us, like that we can be part of shaping how these things are built and make sure that we understand it, at least if we're not actively helping guide it and participate in it? Like, what are the things that we should be thinking about?
Right. Well, AI is just part of the progression of technology. It's the most important and disruptive technology in our lifetimes, but it's just a progression of the abacus to the calculator to Excel. Microsoft shipped Excel, and it didn't come with any geospatial or environmental functionality.
Blank slate tool.
All of you created that. It's going to be the same with AI. So the question is, how do you move from Excel to AI and apply those solutions to your industry? There's tons of generic AI technical tools available, but to make it useful to you, you need to bring your intelligence, your knowledge of the industry and the use cases and the data. And that's not going to happen. No AI is going to wake up one morning autonomously and decide they want to do that. You guys have to do that. But that's an incredible opportunity from a career perspective.
Sure. And, I think it speaks to, we've all had this sense, in this world that over the past 10 years or so that we need to be going through digital transformation, that we need to be doing things in a digital space. We need to have better data systems. We need to have better data attribution. We need to be collecting more information. And it's sort of with this vague sense of like, because it'll help us communicate better, or it'll help us, that there's some positive end out there that we'll have more information. If we have more information, more data, we'll be able to do new things that we weren't able to do before. Up until this point, I think there's been a sense of, okay, we have more data, but we're still just human minds trying to figure out what to do with it.
Right.
And that's just kind of created a sense of overwhelm and some pushback in a lot of instances. I think AI presents the opportunity to use that data to do, like we've been talking about, new things that we weren't able to do before. But then we have to start looking at our data as differently. We have to look at it as really in the next 10 or 20 years, data might become our most valuable asset alongside our people. But our plans that we've developed, our studies that we've done, the things that we've created as a result of our engineering processes, as well as the actual information that's in databases and data tables and systems that we've developed for web applications and other stuff. All of those things take on a new sense of value and a new sense of importance in this future where data is the fuel for everything that we're doing.
Right, precisely, and specifically for Mile High Flood District, because you're getting the data and packaging it up. In the future, you might have to package it up for AI with the end user in mind, who is the model builder. And the model builder needs your data to be labeled and organized in a certain way. And that might impact also the way you process the data from a data science perspective. And you might be able to capture infinitely more data because there's so many more data capture devices, drones and satellites and aerial scans all over the place.
Any camera that's out there in the world that's capturing part of a flood event, could be turned into very accurate data in the future. Or we could even see people in the water and identify triage issues before we would have known about them otherwise.
100%.
And AI is what enables us to use all that stuff.
Yeah, you use AI as part of the data capture process to extract just the data you need, so you're not getting everything.
Mm-hmm.
You populate that data in a repository and label it appropriately, and now it's available for anybody who wants to build a model or access that data as a real-time inference source of information.
Yeah. So what does that mean for, let's just think about, us specifically and all of our peers out there. How do we get from here to there? If we wanted to say, if we collectively got together at the flood district and said, okay, we want to try to help push things forward in using AI in our industry or advanced computing or however we want to define it, what do we need resource-wise? What do we need to be investing in, both from the data standpoint and the personnel standpoint? Like, who are the team members? What are the skills? What are the types of people that we need to be asking? Is our data shaped right and cared for and attributed correctly in order to be able to do these types of things with it in the future? What are those jobs? Who are the people we should be out there talking to about that stuff?
Well, I would say I'll answer that, but the first thing in my mind, the most important thing is to define the use cases. What do you want AI to achieve? How can AI help you accelerate your business, eliminate errors, reduce costs, etc.? Remove the pain from the process. What can AI do that you don't want to spend your valuable human time doing? What are those painful, hair pulling exercises that, humans have to do that they hate doing, and
Right.
You can give that to an AI. There's all sorts of use cases across those different categories. Then once you have a use case identified, prioritized, then the question is, what do you need to build that solution in terms of the data, in terms of the model, and in terms of the skills to produce the final result? The data, I'm assuming you have most of. The model, you don't often need to build on your own, because that's a pretty expensive thing to do. You probably want to start with the model that already exists that does a lot of what you think your model needs to do, and then what's called fine-tune the model based on your data. So teach it some new tricks. So in order to find a suitable model that maybe takes you half the way there, 3/4 of the way there, start in Hugging Face. Also build.nvidia.com. We have models that we've optimized for open source models that our engineers have optimized for performance and ease of deployment. So you can find a model on Hugging Face. You can find a model on build.nvidia.com. The one on build.nvidia.com's faster, let's say. And on build.nvidia.com, you can actually experiment with it for free for a couple of, I think, 20 hours or something like that.
Okay. Hugging Face, just for the folks in the audience who don't know, is an online repository of open source AI models, from image generators and video generators all the way through physics-based models and stuff that we could potentially deploy in various ways.
Yeah. Chances are somebody's already done something along the lines of what you're looking to do.
Mm-hmm.
So check Hugging Face, just has simple search, and go there. And then in terms of the people, like you typically need in an industry like yours where there's tons of data, I assume you want to start with a data scientist to get all the data organized correctly, collect the data, figure out the best pipeline, the funnel to get the data collected, labeled, categorized, organized, fed into your model refinement process. Then you need an AI developer, people who understand how to use the AI tools. And then you need, if you're developing custom applications, you might need to get an application developer that incorporates the AI into like an online SaaS type of application or a desktop application or a modification to ArcGIS Pro or something like that. And then if you're deploying something for example, if Mile High Flood District wants to deploy a service online for all your constituents to use, you would want to have experts in ML ops that understand how to deploy an inference-based solution, how to optimize the use of tokens efficiently, how to leverage on-prem infrastructure or infrastructure in the cloud, how to deploy guardrails, and monitor customer experience through all that process.
Okay. You mentioned ML ops, just to acronym things for our audience, machine learning operations, someone who knows how to deploy software that's built on machine learning practices out in the real world and make sure that it's functioning properly.
Yeah.
So to follow up on that, I think there's an opportunity here to either individually as the flood district and our partners, or collectively as our industry with our peers in other cities, Seattle and Chicago and Houston, and all the folks that are doing this work together. We're solving the same problems in different places. So the fine tuning is different, right? We are applying ours to the South Platte River Basin and to the other small systems that are around it. Folks in Houston are applying it to their, tidal estuary systems, and there's differences in that regard. But we can build potentially together tools that will intake data that can then be used to fine tune a model that allows us to do work basically anywhere in the world, right? And I think that's where maybe there's some use cases that are very, low hanging fruit that we could just kind of do in-house. But I think there's others where if we're actually talking about, these larger type of agentic systems and bringing bigger solutions to bear on bigger problems, where I could see us needing to kind of work collectively or cooperatively with our peers who have similar problems in different places. And maybe they have some part of the expertise, maybe we have some part of the expertise, because it would be a lot, for a little group like ours to bring in 4 or 5 new people who are focused on all this stuff. And we're taking a bet, like you said, that we're focusing even on the right problem,
right?
Because we could invest a lot and then potentially miss the mark, or someone else develops it first. What are your thoughts about how our industry can kind of, bring more resources together and do something impactful working together versus working separately?
Well, 2 thoughts. One, open source development. That solves a lot of the problems. You can continue to iterate collectively a model. 2, any model needs data, and lots of data. Your data is specific to Colorado.
Mm-hmm.
And other regions are specific to their climate. If you pull all this data together, you start to get a nice amount of information for the model to understand regional variances and maybe extract some insights from that. So I think there's 2 things. One is open sourcing the model. Of course, you have to have some agreement on the objectives of the model. And 2, having some sort of collective approach to aggregating the data that's used to train the model. You may want to have regional versions of the model, I'm not sure, or one, global version of the model, so the model starts to understand the world.
Well, I think having, partners partners or mentors, maybe advisors, folks like you guys who understand sort of the broader capabilities and the broader ecosystem of how this stuff works, makes that type of problem and that type of potential project a lot more approachable for folks like us, because we just haven't worked in this technical realm. Even if we have some sense of what the capabilities are, and even the willingness and the desire to go out there and build something new and try it and push the envelope forward. We need partners on the other side who, just like they need us to help kind of guide the domain expertise side of it, we need them to help guide us in the technical side of it and say, like, well, if this is the right tool for that, or this is the right approach for that, or if you need to pivot, you kind of need to have that, back and forth. And I think going forward in the industry, we need more people who have cross training in technical disciplines like engineering and in programming and ML development and other things like that. And I hope that we can encourage, younger people who are in our industry even to get certifications and micro credentials and other things to help at least bridge that gap a little bit to help move those things forward. Because I see that as kind of a stumbling block for our industry moving forward in this domain, is that we just don't have the confidence to feel like we can pull the trigger on stuff while we see the world around us advancing so rapidly. And there's a risk in my mind of us kind of getting left behind a little bit. And then, being in the situation where we're just using whatever tools other people came up with for us. And that's not a really good, feel good situation for folks who are trying to be at the forefront.
Yeah, you don't want to be doing that, because ChatGPT is an incredible tool, but it's not a tool that's designed for you.
Right.
It's not been ChatGPT doesn't have access, as far as I know, to your data.
Right. I hope not.
And it hasn't been refined from a user experience perspective to hone in to exactly what you need and present it in a format that is relevant to your users.
Right.
So, but you could take ChatGPT as a model and fine tune it and build a custom experience around it. You could do that with any large language model.
Yep.
And as an industry, you can decide, well, here's the model and here's the inputs and here's the template for providing those inputs. And anybody anywhere in the world can submit data based on the template to feed into the input so the model can get further refined.
Well, regardless of how far we go in terms of developing, actual products and tools that are related to this stuff, I think an important takeaway for our audience is that we need to be paying attention to what's going on in the world and in the industry and in the world of technology. And we need to start educating ourselves about how these things function, because it's going to be the type of tool set and the type of system that engineering and industry and what to date have been, the kind of hard physical sciences and engineering disciplines. We are going to be working in that world. And just like we have to understand our empirical approaches, like today that we talked about earlier, in the future, we're going to be working in this new space that requires us to understand a different technical way of operating, even if we weren't part of, kind of spinning those things up. So
yeah, let's pull on this thread. It's really interesting. So you have in the past, you had your domain expert who didn't know much about technology.
Right.
And then you had your technology people, your software developers. And often they didn't interact. And most people watching probably don't have access to those software developers. So if you have a cool idea about how you can optimize some sort of process, maybe the best you can do if you're really technical is write a macro for Excel, or maybe write some script for ArcGIS Pro or something like that plugin. But that's super complicated. So AI, it seems to me, is much more approachable than traditional software development.
Because you interact with it in natural language.
Because you interact
learning
with it in
curve is so
natural
low.
language. And with tools like Cursor, or even Claude, anybody could start to create an application with English as the interface. And you could basically type an app into existence. So you no longer have this dependency for that, quote unquote software developer to be in your office and, you have the ability to tell them what to do. Now you can just like you might have in the past, learned a little bit about Excel scripting or Visual Basic to write a script. Now you can learn a little bit about how to use Claude or Cursor to write an app and do
achieve
it yourself.
Something many orders of magnitude more powerful than what you could do with an Excel macro.
Yeah, exactly. And this is called vibe coding.
Yep.
So anybody can do that. It's you can just, you could start like online. It's I don't even think you have to pay to start. And then having a little bit of an understanding of how AI works and stuff. When your company starts to hire like experts who are just going to create custom AIs for the company, then you'll be able to tell them what needs to be done in a language that they understand.
Yeah, you'll have some experience with it.
Yeah. But I think you can be a domain expert and not understand the tech. That's totally fine. Like in a large company, if you want to ease into tech, ease into AI, get more familiar with the tools out there, at least know how to interact with a chat GPT. But a generalized chat GPT type of application is not designed for you. It's designed for, to find out where to go eat on vacation or whatever. So of course it does much more than that, but it's not designed for, environmental sciences. So you might want to build your own version of that and start to experiment with that.
Yeah.
And you could do that on your own. Just start digging into ChatGPT and Claude and understand how they work and how you can tweak them and customize them the same way you can write a script for Excel. And then you can go deeper and deeper until you say, well, I really need somebody to do this full time.
And that's you start to hit that wall,
Yeah.
right? Then you kind of know that's where you need support.
Yeah.
Yeah, I think that's a great way to look at it. We need natural language, just like you interact with ChatGPT, is the way that you're going to be interacting with a lot of these AI systems, regardless of how technical they are. So I think a willingness to get out there and experiment and just get familiar and try new things is really the biggest barrier to entry is yourself, your willingness to just move into that domain. And like you said, it really is easier to work in that world than it is the way that we've done things in the past, where we had to know all the acronyms, we had to know all the processes, the coding frameworks, and the languages. That stuff is no longer a barrier. Folks that don't have that technical training can go in and build an application, and it could actually work and do what they want it to do.
Mm-hmm.
It might not fully get to the end or solve the problem, but it advances everything that we've talked about, both personally and professionally and in the industry, to try to move these things forward. And so we need everyone to kind of try collectively to move in the direction that we're, feeling like is out there somewhere, but we just haven't quite seen it in our realm of civil engineering yet. We might put this back at the beginning of the episode, but can you give just like a little overview of NVIDIA and what you guys do and what your role is in the AI ecosystem? Because I don't think that everyone, despite being the most valuable company in the world right now, or in history, I believe, a lot of folks still don't know who you guys are and what you do. So I would just like to make sure that everyone watching this at least comes away with that.
Yeah, sure. So I'll walk you through it.
Okay.
So everybody knows what a CPU is, I think. Central processing unit. It runs all of our computing devices. We all have CPUs in our pockets, and it's a general purpose processor. The CPU has cores. The cores are like divisions in the processor. Each core can operate independently. So your CPU can do multiple things at the same time. Your typical CPU has like maybe 10 cores, or your laptop 10, 12 cores. So it can do 10, 12 things independently, like run your operating system, run your email application, run ArcGIS Pro, run AutoCAD all at the same time.
Without slowing each other down.
And interrupting each other.
Mm-hmm.
Now, what in computing, and when you take a complex algorithm, it has to fit into one of those cores. Now, what's really and then going into just one core means it has to compute sequentially, linearly, and that could take a lot of time. But with some of these algorithms, what's possible is to break it down to compute across multiple cores in parallel. It's called parallel processing. So, and in some cases, your algorithm can be divided up. You basically copy and paste the algorithm across all the cores you have available, and then you divide the data bits into those cores. Computation happens in parallel, and the result is brought back together. Therefore, the more cores you have, the faster the compute happens. The CPU being designed for brute force operating, keeping the system running, was never designed to have all of these cores, thousands and thousands of cores. It's just architecturally not possible. The biggest CPU, I think, has like 128 cores or something like that. The GPU, which we invented at NVIDIA, is designed to have cores for parallel computing, specifically, not for operating the device, but for doing the math.
Right.
And our GPUs have thousands of cores. And all those cores are doing the calculation in parallel processing, bringing the result back together in real time.
On a single GPU on a single chip. And you're also doing that on the scale of multiple chips, right?
Right, because, it's never enough just to have, you always want more cores.
Right.
So it depends on the operation. Like some of the solvers, you may use like a simple CFD simulation for a small body of water, not a lot of variables.
You might potentially do that on a CPU in some instances.
You could do it on a CPU. Yeah. It may take time. It'll definitely be a lot faster if the code runs on a GPU. 30 times faster, 100 times, it depends, because you're using all those cores in parallel. And in some of those calculations, and this is where, even on the world of CPU, use HPC, high performance compute, which is basically a cluster of servers. In the old days, CPU servers. Each server can have a maximum of 2 CPUs. And traditionally, those CPUs were like, 64 cores each. So you had like 128 CPUs per server. Now you have to power all those servers. You have to have space for all those servers, and you have to cool that space because they run hot. And so this is your typical HPC cluster. And like for complex computational fluid dynamics flood simulation, you might need hundreds of servers. And you're only getting, hundreds times, maybe 128 cores per server. Along comes the GPU, and on one single GPU, you get the same number of cores as that entire server room. And now in one server that's designed for the GPU, you can put multiple GPUs.
Right.
And NVIDIA is architected a way for these GPUs to share memory, so they're all working together as one GPU. But that's still not enough compute for AI. AI wants all the cores in the world. Right. So what NVIDIA has done is figured out a way to connect multiple servers together. And we do this by high-speed networking, InfiniBand, etc.
With
fiber optics, Spectrum X, Ethernet, and switches, and
very cool and very technical advancements in technology, which is why a lot of folks, I think, haven't heard of NVIDIA, or at least aren't really familiar with what you guys do. But that's what's made you guys the most valuable company in the world, is because you've solved these problems that have allowed us to scale compute to essentially close to the level of the human brain, which is what these AI, developers think is kind of the frontier for what they call AGI, or advanced general intelligence. Being able to do more than what a human can do with computing is requiring that level of complexity, and the technology required to give us that level of scalability is something that only one company has ever been able to make.
Well, it's a really hard problem. The brain is a pretty complicated instrument with lots of neurons.
Even if we knew how it worked, which we don't.
Yeah, exactly. Just the same way we don't really know how all the AI models work, but you want to give it everything that you can to get there, which means all these compute nodes, all these cores working together as one brain to solve the problem. And so NVIDIA has not only had to invent the GPU and the networking to connect all these GPUs, we have to work with our partner ecosystem, the companies that are taking our GPU technology, building the servers and building the racks, et cetera, to help them figure out how to scale it all out. But we don't just make the GPU anymore now, because it's not enough. We make the GPU, we make the CPU, we make the networking, the hardware, the cables, the chips.
And the software
stack that powers all this stuff. And now to help industries like civil engineering do cool things on all this tech, we make libraries to make it easier to access our tech. So the core level SDKs to interface with the tech
Software
at a higher
development kit,
levels.
SDK.
Software development kit. So you don't have to write the low level code. That's called CUDA. CUDA interfaces with all our GPUs. But we also have libraries that are domain specific for certain types of solvers, for example, or certain types of mathematical equations, or for certain domains like healthcare, where our libraries make things easier for you all to do some programming work with our stuff. We also have some really interesting packages of software that are meant for software developers to accelerate the work that they do around the physics of the world and simulating the world with physical AI. We have Omniverse, which is for digital twins, and the sort of geospatial version of that, which is called Earth 2, which also allows for weather prediction models to predict the weather, and using the Omniverse technologies visualize the atmosphere information and ultimately how that interacts with the ground plane. That's where it gets really, really interesting.
Well, that's when I first heard you was talking about Omniverse, and it just brought to mind all of the amazing things that we could eventually do if we had a real-time physical simulation of the environment, even a small part of the environment, let alone the whole Earth. That enables us to solve those bigger kinds of problems that we were talking about, which we just never had the computing power to do before, even if we knew what the appropriate solution might be. We could have another episode on just those tools, but NVIDIA is really the supporting infrastructure and ecosystem that allows these end solutions to be built by other partners and players. And that could even be an individual who's just playing around and vibe coding something, can build on top of your guys' tools and then on top of your infrastructure to potentially solve a previously unsolved problem, which I think is a pretty awesome place to be in the world right now. And just for the scaling question, I want people to just be able to imagine this. Training ChatGPT took, I don't know how many of your GPUs that they use, but tens of thousands, I think.
Even hundreds of thousands.
Yeah, for a long period of time. That's the kind of computing power that enabled us to build tools like ChatGPT that was just physically impossible before. And that's really where these breakthroughs, are happening, is on the technical side. So we're really excited to be able to talk to you. You are running up against your time limit here, so we want to give you a chance to say anything else that you wanted to say to our audience before you leave. But we're really, really grateful and excited to have had this chance to chat with you today, Sean.
Yeah, I think, the sky is the limit, literally. And there's so much value that environmental engineers and civil engineers can bring to the world.
Your own son is going into environmental engineering, I should mention.
My son is at CSU, environmental engineering, did his internship at Civil Resources in Longmont, and now he's a senior and is graduating. So I'm excited for his future. I think it's going to be fascinating for how AI plays into all this and makes everybody's life easier and helps us understand the world in a way we just don't today.
Awesome. Well, thank you so much, Sean. We really appreciate your time.
Thank you.